Am I doing work right now? How about now? Am I doing work? Alright, push that wall, go! Move it! Move that wall, move it! Come on! Harder, harder! Yes, Ollie, help them out. Are they doing work right now? Are they doing work? Go ahead. Lift them up! Don't fall! Oh my goodness! What about this? Is this doing work? Not the dog, the two kids. What about this? Is he doing work? So what do you think? Which ones were examples of people doing work, and which were examples of people not doing work? Today we're going to learn exactly what work is and what work is not. Alright, so as you saw two of my three children doing, suppose you push as hard as you can on a brick wall. Have you done any work? Now, you might be sweating, exhausted, you might not have, but you have not really done work unless you've actually moved the wall. So work is defined as a force acting on something as it moves. So applying a force to an object is not enough. You actually have to make it move. For example, this first picture right here, if this person was just pushing, they're not really doing work because there's no movement there. But as soon as that wall, I think he's alive, as soon as that wall moves, work has now been done. So force is measured in newtons. We learned that with Newton's second law when we were talking about force and how we find force. If we want to find what work is, we take force and we multiply that by the distance of how far work has been accomplished. And with that, we get our measurement for work, which we call joules. So if we see this person right here, he's pushing this car, we know there's a force being applied. Remember, force is a push or a pull. And we find force by taking mass and multiplying it by the acceleration that it's moving. And then we take that force, we multiply it by how far he's been able to push that car. And that's how we can get a measurement of work. Now suppose we say that an object weighs 3 newtons. We're saying that 3 newtons of gravitational force are being put on that object. Now remember, weight is determined by gravity's push on us. Gravity pushing us down is what's going to determine our weight, and it can change from place to place in the universe. So if my weight here on Earth would be significantly heavier than my weight on the moon. So when we're talking in terms of weight, we're talking about gravity's push on us. So if I have an object that weighs 3 newtons, that's gravitational force being put on that object. So newtons are a measure of both force and weight. We would use a spring scale to measure an object's force in newtons. And this is what a spring scale looks like. If you multiply the object's force by the distance the object travels, you'll determine the amount of work that's done. Again, the unit that we use to measure work, we call it joules. So here's an example right here. If I lift an object that weighs 100 newtons, and I lift it up 5 meters to get until I'm standing, I've done 500 joules of work, or Newton/meters, okay, of work. Again, I would take 100 and multiply that by 5. This one's very simple. Just take the amount of newtons, multiply it by the distance that it travels to get the amount of work. Again, we call that joules, and we would just list that with a J. The newtons we know is an N, and then J for work. Here's another example. If I'm pushing a box against 20 newtons of friction over a distance of 25 meters, this also equals 500 joules of work, because I have 20 newtons, again, of friction. You see how the floor is, there's a lot of friction there. And I multiply that by the 25 meters that I've pushed it. 20 times 25 will get 500 joules. Okay, now let's say that there was no friction here. Is this number going to be the same the 20 newtons of friction. Let's say we're pushing it on ice. No, it's not going to be the same. We have to take into account the friction there. Now, because work equals force times distance, there's two principles that apply to this. First one here, applying a greater force over a shorter distance involves the same amount of work as applying a lesser force over a greater distance. So let me give you an example. So here would be an example. Gunnar is holding 20 pounds of weight. And with his 20 pounds, if he walks from where he's at, start walking to me, to stop this spot right here, it's the same thing as if I have Gunnar now from way back there carrying now 5 pounds of weight. He's now walking twice the distance as he was. Keep coming. Perfect, stop. Twice the distance than when he carried 20 pounds. He did the same exact work, but because the newtons were different, he had to extend the length that he walked in order to do the same amount of work with the lighter weight as he did with the heavier weight. So again, we can go from, let's go back a little. Jumped ahead. Again, applying a greater force over a shorter distance involves the same amount of work as applying a lesser force for a greater distance. So when Gunnar carried the 20 pounds, he walked a shorter distance, but he had the same amount of work put into it when he was applying a lesser force, the 5 pounds, over a greater distance. He did twice the amount covered twice the amount of distance. Okay? So how is it that we can make work easier for us? I am all about how can we make things easier for ourselves. If I don't have to put in as much work and I get the same amount of results as if I had to put in a lot of work, I'm going to take the easier route most times, and I think you guys can agree with me on that. So how is it that we can do more work with less effort? Well, we have these awesome things called machines. And a machine is any object that makes work easier. Praise the Lord for machines. Simple machines do not reduce the amount of work done. However, a simple machine makes that work easier by strengthening the force used to do the work or by changing the direction of the applied force. And we have 6 simple machines that we're going to be going over the rest of the school year. We have an inclined plane, which we simply call a ramp. We have a wheel and axle. That's basically having wheels, which is amazing. We have pulleys, and there's all different types of pulleys. You guys, for those of you that went to St. Augustine, you guys remember going to the old village and they had a whole setup of different types of pulleys, and some of it, the simple ones, made work a lot harder to do than some of the more complex ones that we had. All right. Next one, we have a lever. This is the first one we're going to be talking about. And we also have a wedge. And we have the screw. And all 6 of these are considered simple machines because why? They are an object that makes work easier. So remember, a force, again, is a push or a pull. And this force that's applied to a simple machine, we call this the effort force, or simply we just call it effort. The resistance force, or what we call resistance, is the force that works against the effort. So sometimes the resistance is a push or a pull, but often it's the weight of an object being moved. So if we look here, we have the resistance over here because there's a weight of an object on this seesaw. The effort would be right here where we have to push down. This is where we're putting all of our effort in order to move the resistance. So again, we're going to be looking at those six simple machines, and here are some simple examples of what each of these are. Again, we're going to first look at levers. And all machines, even our complex ones, those are the ones that have multiple simple machines in them, they're usually made, again, of one or more of these simple machines. And machines are simply things that make work easier. I don't know about you, but I love things that make work easier. So when we look at levers, we're going to look at how different types of levers, and we're going to see how they make work easier, kind of like these wheel and axles that are going by. Anyways, answer the questions at the bottom of the video and email them back to me, and that will be your daily grade for today.